Good afternoon, everyone. In today's digital control systems technology lecture, we are going to be focusing on feedback control system design. So, in the previous week or the week before, we in the introductory lecture we talked about control systems and basics of control systems, and we touched upon different types of control systems or different types of control system designs or architectures. And one of the ones that we identified, or the two that we particularly identified, are the open loop control systems and the closed loop control systems. So what we are going to be focusing on today is the closed loop control systems or the feedback control system. So, when we think about a control system in general, this is something that we again discussed briefly in the previous week as well, previous lecture as well, particularly in the introductory lecture. The idea of a control system is it is something, it is a controller, it is something, a system that will take some inputs. So, it will take some inputs, and the input will specify what we expect out of the system. So, we'll specify the desired response. So, we will have some intentions, we will have some ideas, and we would give that as the input to the system. And then the control system will control the underlying system. Say, an example that we touched upon is an air conditioner. And if it needs to control the temperature of a room, then controlling the temperature is the output. So the input is about setting a temperature in degrees Celsius. Then the control system will manage the cooling system, the fan system, and so on, and try to get the desired output. So the output will be produced by the control system, and then there may be an actual response as well. So sometimes we may want to get a particular temperature out of the air conditioner, but it is not yet producing that desired value. So say, for example, we set 24 degrees Celsius, but it is still at 26 degrees Celsius. So there may be a difference between the actual response and the desired response. So that is the basic idea of a control system. It is something to which we can give some input and indicate what we expect out of the system, and then the control system is the one that is going to manage and try to get that output for us. Sometimes we may get the desired output, sometimes we may get a different output that is different from the desired output, but that is the basics of a control system. So a good example, particularly thinking of the recent weeks, we had an issue in the country, so to speak, where the energy load was not sufficient enough for the generators, and we had some issues as a result of that. So again, here the load or the requirement from the end users creates the request or the input, but the controller is the one that is going to make changes to the actual generation system to indicate what amount of generation that needs to happen. So for example, if we indicate or if we identify the load is increasing, then the controller may have to give certain control commands to make the generator run faster or produce more energy as a result. So that is what we would try to do with a control system. So the actual device, we would call that as the plant, and the controller would be the device that is actually controlling, giving control inputs or control commands. So that is the differentiation that we have to see here. So when we talk about control system, we are mainly talking about this logical controlling part, not the actual plant itself. So this is the control system that we are mainly focusing on. Then Another thing that we can see regarding the responses and how control systems would function. For example, let's take the example of the air conditioner here. So, in the air conditioner, let's say the current room temperature is at uh, 30 degrees Celsius, and we expect it to bring it to say 24 degrees Celsius. So that is the expectation. So the input command is this 24. So that is the desired output. Then the system will have to function in a manner to bring the temperature back to that particular point. So we will have a particular period that we would identify as the transient time or transient response, through which the temperature is still going to change. It is going to go down from 30 to 24. But after a while, we may reach a point where there's no longer we are having any change in the system. So that steady point is what we would call as the steady state response. So that is the steady response that we get as a result of the process. But sometimes what we may see here is there is a gap between the actual input command and the steady state response. So that difference we would identify as steady state error. So for example, if we want to get the temperature down to 24 degrees Celsius, but for some reason we can only get it up to 24.5, then there is a 0.5 degrees Celsius difference that is steadily keeping up. So it is not changing anymore. So it is not in the transient period, it is in a steady period, but there is a slight difference. So that we will identify as the steady state error. So what we would want to achieve with any control system is to go through this transient response time and achieve a steady state response, or having a steady result. So we don't want temperature to go up and down, up and down. We want to keep it at a particular desired value. And we want to reduce the steady state error as much as possible. We want to bring it to 24 as much as possible. If that is not possible, we want the difference to be as minimum as possible. So these are the two things that we would try to achieve with these control systems. So when thinking about different types of control systems, we can, as we mentioned in the previous lesson, we can mainly categorize. The two main categories are open loop control systems and closed loop control systems. So we will briefly look at what open loop control systems are. So with open loop control systems, what we have here is we will start with the input command. So whatever the input command, we will start there. Then it will go to the controller. So that's the logical device that is going to do the controlling, that is going to produce the control input. And then it is going to act upon the actuators and the actual plants. Then we can have sensors to detect the change, but that's about it, that the output is still there. Let's look at it from the example of a temperature control system. So here the input command would be say 24 degrees Celsius. Then the controller will get that input and it will produce a control input. So that would be how, for example, how fast the fan should operate. So the fan would operate at say 2000 RPM, whatever, just a random number. So the fan would operate at a particular speed. Then based on that, we are getting some output happening. But for example, if the outside temperature changes, then that is also going to impact upon the achieved temperature there. we can have a sensor here to sense what is the current temperature and say, okay, currently it is now at 26 degrees Celsius. But in the case of open loop control system, the main point here is the output variable that we got here, the output of 26 degrees Celsius, is not going to impact the input variable. So whatever the input that is being produced by the controller is not aware of what is happening at the output point. It is only taking this command as the input and making changes to the devices here. It is not considering the output that it is producing. So whether the room temperature is 24 now, or is it 26, or is it 22, doesn't matter. The controller will still function in a similar manner. It is not going to be impacted by any external disturbances. It will keep on working. So the problem with this approach is sometimes it will not be able to react to any undesirable disturbances. Say, for example, if the room temperature suddenly increases, if somebody is opening the doors quite a lot, so the outside hot air is coming in, or the overall outside temperature is increasing. In those situations, this type of a system will not be able to react because it is functioning with a set value. It is always going to set the speed at a particular value when the command is 24 degrees Celsius. So that is one of the issues that we would find with open loop control systems. But on the other hand, it will also not be disturbed. So the not being disturbed can sometimes be an advantage as well. Say, for example, even if external inputs are happening, things are impacting on the system externally, it is still not going to change what it is doing, the rate it is functioning, all these things. It is not going to change even if outside forces are impacting on it. So in that case, it could also be a good thing. So there would be certain applications where such an open loop system could be advantageous. But in some other places, we may desire a closed loop system. So now when we think about closed loop systems or feedback control systems, here the main difference is whatever the output variables will also be taken into account for the controller. So whatever the output that is being produced will also be considered as part of the input to the controller. Say, for example, if the outside temperature is measured as 26 degrees Celsius now, then that information will be passed on to the controller again. Then the controller can compare that and see whether it still needs to cool the room, or it now needs to heat the room, or how much it needs to cool or heat. So again, that input or that feedback will be happening from the output to the input again. So that is the basic idea between the feedback or main difference between feedback control systems and open loop control systems. So to do that, what we need to have is at the output point, we should have a way to measure an output. So we should have some sensors. For example, in the case of an air conditioner, we should have some temperature sensors to sense the current temperature inside the room. So that can be measuring the output, and then that can be fed back into the controller. And the controller itself will have to do some computations here to see what is the difference between the expected or the reference input and the actual output, and see what are the differences and how it can change that. So that is the basic idea of a closed loop control system or a feedback control system. So if we can see here, so the main differences that we can see here is the command input will be there. So this is, we will have the command input there. So that is where we will say 24 degrees Celsius. Then that would go on to the controller. The controller is going to produce the control input for the motors, for example, and that will act upon the actuators, and that will produce the cool air in the room. Then at the end we would have some sensors, and at the sensors we will do some measurements and get the output temperature. So now that is measured as 26. So now we will bring that measured output back to the controller as another input. So now what we will have is, we will have two inputs. So we will have an input of 24 that is coming from the actual command, and a measured input of 26. So now what we can do is we can compare these two and compute what is called the error. So we will compute the error value, and the error value will say there is a difference of 2 degrees Celsius. So that would mean the controller still needs to cool the room more by 2 degrees Celsius. So then that can still impact, or that can give further instructions to change the input, and it can still keep on functioning. So the main difference that we have here is this path of the feedbacks. This feedback path that is coming from the output back to the front, or the front of the chain, or the command chain, is the main difference in a closed loop system. The advantage with this approach is it can reject any disturbances that are happening to the system. Say for example, if the room temperature suddenly increases because outside hot air got in, and the room temperature has increased back to say 28 degrees, now again that information can be fed back into the system, and that can be detected as an error, and the controller can still try to cool the room much more than it is currently doing. So it can change the behavior of the system, it can change how much a system is working, how fast it is working, and so on, based on the output it is generating. So that is the main idea behind the closed loop system. It can react to disturbances. But reacting to disturbances, as we said with open loop systems, reacting to disturbances can sometimes be undesirable, because if things are changing quickly, then the system will also react to that much quicker. So then it can become an unstable system. So it is increasing, decreasing, increasing, decreasing. So based on what is happening in the outside world, it may be impacting the system, and it can change quite a lot. And that type of unstable change is not something we want in some systems. So again, that is something that we would want to avoid, and there are some mechanisms to do that. We will discuss about those also later today, and also in the upcoming lectures. So now let's think about an example. So let's think about this example. We have a simple robotics device. What it has to do is it has to move towards the wall and stop at 1 meter distance. So let's say if the device is currently at 11 meters, the current distance from the wall is 11 meters, and it has to move towards the wall and stop at a 1 meter distance. So that is what it needs to do. So what are the two approaches that we can have with a closed loop approach and an open loop approach? You can think of this even from a sort of day-to-day life example. Say you have to walk towards the door, and you have to stop at the door, if that is what you need to do. So then, if that is the task at hand, how do you do that? What would be the approach in an open loop system, and what would be an approach in a closed loop system? So if we think from a real life perspective, what can happen is, say for example, you have to go 10 meters here. So we are at 11 meters distance, and we have to go up to the 1 meter distance. So the length that we need to travel here is a 10-meter distance. So in a open loop system, what we do is, in the open loop system, we give it the instruction to say travel for 10 meters and stop. So that is the only instruction that we are going to give, and it is going to do that particular instruction. But in a closed loop control system, we will not give the instruction like that. We will have a measurement way to see how far we are from the ball. So we will initially measure, okay, how far we are. So we are now at 11 meters, so we can still go forward. Say we have gone another 5 meters. Now we will measure and see how far we are from the wall. We are now at 6 meters, so we can still keep on going. We will measure again, and we are now 2 meters away, so we can still keep on going. But now we have to stop at a particular point where that is 1 meter. So that is a problem that we may face. That is, how do we stop at that point? But that we can discuss a bit later. But other than that, the main idea is we keep on measuring the error, and we will try to bring the error down to 0. So that is the main idea behind the closed loop control system. So we are at 11 meters, we will measure 10 meters, keep on going, and until we reach that 1 meter point, we will keep on measuring and changing the input to whether to go or not to go. So that is the basic idea behind a closed loop control system. So when we think about closed loop control systems or feedback control systems, these are one of the most common ways, or even sort of the natural way systems work. Even as we said, even when we are walking, we don't normally measure how far we need to walk. We detect any obstacles and see how far we are from the obstacle. We try to work towards that, and then based on those changes, we change our behavior and keep on walking. So it is similar to that. So the feedback control system will keep on measuring, keep on assessing the environment, the situation, and then react according to that. So even things like the global carbon cycle, where even such a larger sort of broader systems, even they can be categorized or considered as closed systems or closed loop systems or feedback systems. So that is a very common approach or common way things happen in the environment. So if we think about a more digital example, an example of a feedback system using a digital device, uh, a good example could be a speed control system of a vehicle. So in this example, what we have is, we have a vehicle that would be riding, or we are driving at a particular speed, and we want to keep that at a particular speed. So if we want to keep like a cruise control or a steady speed maintaining system, so then whatever the output speed will be sensed, and then that output speed will be given back as the input to determine how much throttle should be given to the vehicle engines to run. So if the speed is below the expected speed, then we will increase the throttle. If the speed is above the limit, we may decrease the throttle. So that is the basic idea again, how we would use these control systems. So let's say if we want to achieve 50 kilometers per hour, if our desire is 50 kilometers per hour, then what we are detecting is 30. So now we can change. We still need another 20 change. But if we achieve 55, then we need to reduce the speed by 5. So we can still do changes based on what the output is sensing at the end. So now, when we think about a computer control systems or a control system that is built as a digital device, we can identify a number of components, number of major components here. So what we would have is, say, we would start with the actual system itself. So whatever the air conditioning system or whatever, that is the system that we are talking about, and that is the one that may be impacted by the external disturbances. So any changes in the room temperature is the external disturbance. Then we would have sensors like a temperature sensor to sense the information uh, about the room temperature. So then the output is happening. Then that information will have to be sometimes converted back into a analog to digital converter into something that is understandable by the computer. So we may have to do some conversions, and at that point whatever the control input or the operator input also will be given. So that is where we are setting a temperature for the room. Then whatever the necessary outputs for that motor, the compressor and so on will be produced, and that output may have to be converted from a digital value to again a analog input, which can be given back to the actuators to make the changes to the system. In addition to this, when these communications are happening between these systems, we would classify these into sort of two broader parts. One is the process component, so that is the actual system that is working, and the controller component, so that is the main controller part. So when the communication is happening between these two, between the controller and the process components, we may also encounter noise in the way of communication noise. So this is something with data communication, electronic communication, this can happen. But overall, these are the common components that we would encounter in a digital control system or a computer controlled system. So this one again indicates a much broader view of few other common things that we may encounter in such systems. So we would have the plant or whatever the actual device that is producing the output, and we would have some sensors to sense the outputs that are being produced. Then we may have to do analog to digital conversion and feed it into a computer or a microcontroller. And there we may have certain control algorithms and other control models. We will look at some of these later, but it will use that in conjunction with the reference inputs that is given and produce an output, which will have to be again maybe converted back to an analog signal and then sent back to the actuators. So that is the main flow of control happening in a closed loop control system. Then one of the concepts that we would come across with when we are using control systems is what is called compensation or system compensation. The main idea of system compensation, it is basically if there is a device, if there is a plant, and if we have a control input or if we have a desired output, the input that we give to produce that difference. So if we are at a particular temperature value and we want to reach a different temperature value, then we have to set the input accordingly to reach to that required temperature value. So that difference or achieving that difference is what we identify as compensation. So in closed loop systems, compensation can happen using self-tuning, or it can detect these changes and it can compensate for itself. Whereas in open loop systems, that may not happen. So depending on our requirements, the system may compensate slightly differently from system to system. But the main idea is how we achieve that change that we need, and that is what we call as compensating. So when we think about compensation, again, we can think about few different ways these compensators can be designed, or compensators can be designed. So again, that can depend from system to system. The approaches that we may take would differ, but the main idea is it is the additional circuitry that will have to be included with the control system to address any sort of deficiencies in the performance. So it is the additional circuitry that is there to account to any differences that we are encountering. So again, there are a number of types: cascade compensation, we'll look at some of these later as well, feedback compensation, output and input compensations. In terms of the overall compensation designs, again, we have few different approaches, what are called PID control systems, PID control designs, control compensation design, phase lead, phase lag, and phase lead lag compensation. So these are the ones that we will briefly touch upon, but PID control is the one that we will be discussing in more detail as part of this course, and that will form the most of the content throughout this course, including your project submission as part of this course will be based on PID control. So if we look at PID control briefly for today, and we will discuss PID control in much more detail next week, the idea of PID control is having three different components, and PID is proportional, integral, and derivative component, and each of these will help us to achieve a more stable output, a more desirable output in a closed loop control system. So proportional is the idea behind proportional is it is proportional. So if we have a particular output happening, so whatever the response will be proportional to that. Then integral, again, that is something that you may recall from your mathematics lessons. Integration is actually the total value of something that is happening over a period of time. So integration would be based on that. And derivative is, again, if you recall your mathematics, it is the rate of change something is happening. So if something is happening quickly, then the compensator should also react quickly. So that is the idea behind derivative. Again, we will discuss PID control in much more detail next week. So how we may implement PID control is inside the controller itself. We will have these three components, the proportional, integral, and derivative components as three components, and then we may combine those outputs to produce the desirable output into the system. There is actually a mathematical representation for PID control that is accounting to the inputs, errors, and the outputs that we produce as a result of that. Again, as I said, this is something that we will discuss a bit more later in next week's lesson. But as a reminder, have a look at your mathematics lessons on derivation and integration, and that would be useful in understanding this part of the lesson next week. So the idea of using a PID control, or three-part PID control, is actually trying to solve some of those issues that we earlier identified with closed loop control systems. So that is, we said, because of these disturbances that can happen from the outside world, sometimes it may lead to not producing a stable output. So, or it is not achieving a steady state error or zero steady state error, or how quickly it can respond. So, these are some of the different things that we are trying to achieve using a three-part PID controller. So, the P component, the proportional component, will be the main controller part that is responding to the system. Then the steady state error part or the integral part will reduce the steady state error, and the derivative part will reduce the or provide a rapid response. For example, if our air conditioning system, if we go back to the air conditioning system, what we need to do is say our room temperature is 30 degrees Celsius and we want to go to 24 degrees Celsius. So now the difference is 6. So we would use that 6 directly as the proportional component. Then over time, when the temperature is now reducing, the amount that is reduced so far will be considered as the integration, and we would keep on adding on to that to bring that to a zero value, the change to 24. We don't want to stop at 24.5, or we don't want to go below 24 either. So do that, we will use the integral part. And then, for example, if suddenly the temperature increases again to say 26, we want the controller to function as quick as possible, and that would happen using the derivative part. Again, we will discuss in much more detail how these things would work in the next week's lesson. So with that, our main discussion into feedback control systems is concluded, and the important point here now is about your group projects. So the main idea of the group project is that you will be building a closed loop control system or a feedback control system, and you would be implementing a PID control compensator as part of the control system design. So at this stage, the main expectation is that you submit your group assignments or selection of group members, and that you are supposed to submit these by this week. And after that, you can start thinking about different project ideas as to what are the different ways you can build these control systems and so on. Again, maybe with the lecture next week on PID control, you will get a bit more idea as well. So that is what you need to do about the projects. So first task now is selecting a group, and you can post your group details on LMS. And then next week, we will start thinking about different project ideas for project groups. And then we will do this as a proper project through your course, in your course. So you will have to do a project proposal, and then we will be evaluating that and see if it is a suitable project. If not, you will have to change your project idea. And then you will have to design the system. You have to do the system design, circuit design, and so on. And only finally we will go into building the system or building the device itself. And hopefully by that point we get to come back to the university to do those things. Other than that, focus on the current thing of setting a project and thinking about some project ideas. So are there any questions about the project or anything else for the day? And as always, you can ask questions on messaging or LMS or anything, that would be fine. So if there's nothing else, we may conclude the lesson for the day. Thanks for joining in, and see you next time.